Good morning, students. Welcome to the lecture. So, now our topic is electric field due to point charge. In our previous lecture, we learned about electric field and the numericals related to that. So, I think we do a quick revision about electrostatics. So, we start from electrostatics. We learn about all the numericals related to that, and then we learn about the principle of superposition, and after that we learn about electrostatic equilibrium. Okay, and after that we learn what is electric field. Okay, and electric field, a line of forces. So point always kept in mind is electric field can be defined as a space surrounding a charge in which another static charge experience a force on it. Okay, so this is the basic definition of electric field. After that, we will learn about electric field intensity and the electric field due to continuous charge distribution. So now our today's topic is electric field due to point charge. So students, what you understand by electric field due to point charge? So we learned the formula of electric field, which is E is equals to kq upon r square. But in the vector field, we use the formula E vector kq multiplied by r cap. Okay, so this is the formula of electric field in a vector form. Okay. So there is another formula related to electric field, which is E vector is equals to kq upon r cube multiplied by r vector. So here r vector represents position vector of test point with respect to source charge. Okay, what r vector represents? Position vector of test point with respect to source charge. And how to find r vector? We know the values of k, q upon r cube. R cube is the distance, q is the charge, k is the constant. But r vector, how to find r vector? So r vector is equals to r vector test point minus r vector due to source charge. Okay, we find r vector with the help of this formula, and we will put the value of r vector in that formula. So we have three formulas of electric field. Okay, so these formulas are electric field due to point charge, and this formulas only apply due to point charge. Okay, there is a numerical related to this formula. So find out the electric field intensity at point A is equals to 0, 1, 2, and due to point minus 20 microcoulombs situated at point B, which is root 2, 0, and 1. Okay, so this is the question. And what we have to done in this question, we have to find the electric field intensity at point A. Okay, we have to find the electric field intensity at point A. So the formula is E is equals to kq upon r vector the whole cube multiplied by r vector. Okay, so we have to use this formula in this question. So first of all, we have to find the r vector. So how to find r vector? Position vector of A minus position vector of B. So we have given position vectors. So root 2 I cap plus j cap plus k cap. If we minus position vector of A into position vector of B, we will get the value minus root 2 I cap plus j cap plus k cap. That means we have to minus these dimensions from these. Okay, and we will get this value. So r vector is equals to under root 2 ka whole square plus 1 whole square plus 2 ka whole square. And we will solve this. We will get the value 2. Okay, we will get this value. Now what we have to do in this question, we have to find electric field intensity, and then the formula of electric field intensity is E is equals to k. The value of k is 9 into 10 raised to the power 9 multiplied by minus 20 because the value of charge is minus 20 microcoulomb. Due to this, we will multiply the value of 20 from 10 to the power minus 6 upon the distance. The distance is 8. Why? Because we have the value of r vector is 2 and because of the formula r vector ka cube, so the cube of 2 is 8. So here 8 multiplied by r vector, and r vector is minus 2ik plus j cap plus k cap. Okay, I hope students you understand. So now if we will solve this equation, we will get minus 22.5 multiplied by 10 to the power 3 multiplied by minus 2i cap plus j cap plus k cap Newton per coulomb, Newton or coulomb. Okay, so I hope guys you understand how to apply this formula. Okay, how to find position vectors. So moving to our next topic, which is for infinite linear star. Okay, so now we learn how to find electric field for infinite linear stars. So you can see the diagram over your screen. This is the rod, this is the charged rod, and the positive charge are distributed on that rod, and there is a point P. Okay, you can see this. There is a point P which is situated at d distance from this rod, which is minus infinity to plus infinity. Okay, and this point P which is situated at d distance from this rod, and we have to find the electric field due to this rod on point P. So what is the formula of infinite linear charge? Okay, you have to learn the formula of infinite linear charge, which is equals to E is equals to 2k lambda upon r. Okay, the formula is 2k lambda upon r. 2k lambda upon r. Okay, now graphic representation of infinitely long line star. So this is the graphical representation due to the infinite long line charge. This represents the electric field. Okay, and this represents distance. Okay, this is the graph between electric field and distance, and this charge is uniform. The graphic representation of infinitely long line charge is like this. Okay, hope you remember this. So the question which is based on infinite linear charge is you have to use the formula E is equals to 2k lambda upon r in this question, and the question is two parallel infinite line charges with linear charge density. Lambda is density is plus lambda and minus lambda coulomb centimeter. So r placed at a distance of 2r in free spaces. So what is the electric field midway between two line charges? We have to find the electric field midway between two line charges. These are the two line charges. Okay, so we can solve this question on a blank sheet. Okay, we are taking a blank. Okay, so the two line charges are given. We make the we draw a line. This is infinity to minus infinity, and this is also minus. Positive charge is distributed on this rod, and negative charge is distributed on this line, infinite long line charge. Now what we have to do, we have to find the electric field. So if we are coming to the question, two parallel infinite line charges. So in this diagram you can see these are the two parallel infinite line charges with line charges densities The densities is lambda, okay, plus lambda and minus lambda. So are placed at a distance of 2r. Okay, the distance of these long line charges 2r. Okay, then in a free space. So what is the electric field midway between the two line charges? So to find the electric field, what we will use? Electric field. The net electric field due to both charges is E is equals to E1 plus E2. Okay. So the value of E1 due to the formula of linear line charges is 2k lambda upon R plus 2k lambda upon R. Okay. Due to this charges, the electric field intensity is 2k lambda upon R plus 2k lambda upon R. So if we add this, we get this value 4k lambda upon R. Now, we all know that what is the value of K? The value of K constant is 1/4 pi upon epsilon naught. If we put this value of K in this equation, what we will get? We will get 4 pi epsilon naught lambda multiplied by R. So 4 is cut by 4, and what we will get? We will get the value of pi upon 4. Sorry, this is lambda. Yes, we will get this value, which is lambda upon pi epsilon naught R. Okay, so the option 1 is correct. Okay, this option is correct. Okay, students, what we are done in this slide, we take a two line charges, which is positively charged and one is negatively charged, and we have to find the electric field due to both the charges. Okay, so the formula of electric field for infinite line charges is 2k lambda upon R. Okay, so now we find the value of net value of electric field, which is 4k lambda upon R, and if we put the value of k1, which is 1 upon 4 pi epsilon naught, we will get the value lambda is equals to pi epsilon naught R. So the option A is correct. Okay, students, I hope you understand this point. Okay, so now we are moving to our next topic, which is electric field on the axis of uniform charge ring. Now, students, we learned how to find electric charge or electric field on the axis of uniform charge ring. Okay, so what you are seeing in this diagram says that there is a positive charge ring. That means the positive charge is distributed over this ring. Okay, so the distance between center to point P is R. So the value of electric field on the axis of uniform charge ring is kqx upon r square plus x square p power 3 by 2. So this is the formula of uniform charge ring. What is the formula? Kqx upon r square plus x square p power 3 by 2. And we also have to know that the electric field on the center of this ring is 0. Okay, electric field on the center of the ring is 0. Okay, so this formula is for uniformly positive charge ring, and which is situated at r distance from point P. And if we want to find electric field on point P due to this positive charge ring, is kqx upon r square plus x square p power 3 by 2. Okay, and the graphical representation of this uniformly charged ring is this. So we can see that the E maximum, that means the value of electric field is maximum at this point. Okay, we can say that the value of electric field is maximum at this point, which is R by root 2. Okay, which is R by root 2. Okay, so this is the graph between electric field and distance. R represents distance. Okay, so I hope you understand the graphical representation of axis. Okay, so the graphical representation of infinite long line charge and the graphical representation of uniformly charged ring. Okay, E maximum R by 2 and E is equals to 0 at the center of the ring. Okay, okay. So I have a question for you guys, which is based on this formula. Okay, there is a positive charge which you can see in the diagram. Q is distributed uniformly over a circular ring of radius capital R. A point particle having mass m and a negative charge minus Q is placed. This minus Q is placed on a ring on its axis at a distance x. At a distance x from the center, find the force on a particle assuming x is very greater than r. To find the time period of oscillations, we have to find the time period of oscillation of the particle if it is released from there. Okay, if it is released from there. So what we have to find in this question, we have to find the time period. Okay, time period of oscillation of particle. So, okay, so we need a blank. Now, we have to solve this question. So, in this question, the force on this uniformly charged ring will be, okay, we will make a diagram of it. This is the ring, okay. There is a ring like this, okay. So, this is a Q charge and this is the x distance, and we will have to find the time period, okay. And this is minus Q charge and this is E. Okay, so if we have to find the force on E point is equals to QE. Okay, it's equals to QE and it is towards the center. Okay, it is towards the center. So, what is the value of F? Now we will put the value of E, which is KQX, KQX upon R square plus X square. This is the formula. Now we will put the value. So the value of, but before this, we have to know that R is very greater than X. Okay, R is very greater than X. So we can assume R square plus X square is equals to R square. Why? Because in comparison to R, the value of X is very small. Okay, so we can say that R square plus X square is R square. So we put this value on this equation, and then what we will get? We will get Fe is equal to the value of K is 1 upon 4 pi epsilon naught K Q X upon R square power 3 by 2, and the value of K is 1 upon 4 pi epsilon naught Qx, which is, this is capital Q, not small, Qx upon R cube. Okay, we will get this value, and this value is towards the center of the sphere. Okay, what we are done in this question, we have to find the force. So what is the force? F is equals to QE. So we know the value of electric field due to uniformly charged ring, which is KQX upon R square plus X square T power 3 by 2. So we will put the value of E, and then according to the condition of the question, that is R is very greater than X. So we will take the value of X like R square plus X square is also equals to R square, because in comparison to R, X is negligible. Okay, so we will put the value of X 0. Then if we put R square, then what we will get? KQX upon R square T power 3 by 2, and after we will solve this, we put the value of K, which is 1 upon 4 pi epsilon naught, and the remaining values are Qx upon R cube. Okay, so this is the value of Fe. So since, okay, on the next slide, what it's saying, since the restoring force, what is this? Fe is represent restoring force. Okay, restoring force. So therefore, motion of the charged particle in SHM. Motion of charged particle in SHM is represented by T is equal to 2 pi m by K, which is equals to 2 pi, and we know the value of K. How we will get the value of K? According to this equation. According to this equation, we will find the value of K now, because here Fe is equals to K. No, it is not like that. K Q X upon R cube, which is equals to Fe. Okay, so we can put this value in this equation. So what we will get if we put this value in this equation, KQ upon 4 pi epsilon naught R cube. Okay, and this is the value of T. So after solving this, what we will get? 6 pi cube epsilon naught m R cube upon T power half. So after solving this, we will get 16 pi cube epsilon naught m R cube upon Q, capital Q and small q, T power 1 by 2, which is half. So this is the answer of this question, which is time. We have to find the time in this question. The time period of oscillation of particle if it is released from there. Okay, so the value of time period is 16 pi cube epsilon naught m R cube upon capital Q multiplied by small q T power half. Okay, students, understand what we was done in this question? First of all, we have to find the restoring force, which is equals to Fe equals to QE, and it is towards the center of the sphere. And according to the question, R is very greater than X. So we take the value X equals to 0, that is negligible and compared to R, and we will put this value in this equation, and what we will get? We will get this value. Okay, so according to the condition of the question, we have to find time. So according to SHM, what is the value of time? 2 pi under root m by k, and after solving this, we will get our answer. I hope students you understand this question. This kind of question are putting in the exam. Okay, so in exam point of view, this is also very important. Coming to our next topic, which is electric field due to uniformly charged spherical shell. Okay, which is electric field due to uniformly charged spherical shell. What is the formula? Spherical shell. According to the spherical shell, you can see this shell now. So it is same as that the formula of electric field. What is the formula of electric field? KQ upon R square. Okay, KQ upon R square, and it is also same as that. How? For the outside point and point on the surface, the uniformly charged spherical shape behave as a point charge at the center. How it is behaved like point charge? Because there is a point outside the center, outside the sphere. So for outside point, okay, what it said? For outside points and point on the surface, the uniformly charged spherical shell behave as point charge. Okay, if the point is on spherical shape, all it is outside the spherical shape, the points are behaved like point charge. Okay, understand, friends? What it said? For the outside points and point on the surface of uniformly charged spherical shell, it behave as a point charge which is placed at the center. So that's why we can say that is equals E equals KQ upon R square, and in this the value of capital R is greater than the value of small r. Okay, you can see in this diagram, and E is equals to 0. So with the help of this question, we understand this equation. What is this equation? So the question is, figure shows a uniformly charged thin sphere of total charge Q and radius R. A point charge Q is placed or is situated at the center of the sphere. Consider a distance CA is equals to R and BC which is equals to R. Okay. What is asked in the question? Figures show uniformly charged thin sphere of total charges Q. Okay, and radius is R. A point charge Q is also situated. Okay, this is the point charge Q, which is also situated at the center of the sphere. Consider CA, which is this. CA is equals to, consider C is equals to R. Okay, and BC is equals to R. Okay, this is R or R. So what we have to find in this question? We have to find force on charge Q. First, force on charge Q. Second, electric field intensity at point A. Second, electric field intensity at point B. Okay, so you can say that force on charge Q is 0. Why? Because we learn now electric field is 0 inside the center of the sphere or center of anything. So we can say that electric field at the center of uniformly charged hollow sphere is equals to 0. So force on charge Q is also 0. What I'm saying, electric field at the center of uniformly charged hollow sphere, this is uniformly charged sphere, and the electric field at the center of uniformly charged hollow sphere is equal to 0. So the force is also 0 on the center of the charge. Okay, I hope the first point is very clear to all. Coming to the second point, electric field at A. We have to find electric field at A. What is the value of electric field? KQ upon R square. But we have to find electric field on a sphere. Okay, so the value is EA vector is equals to EA sphere plus EQ. How? Because electric field intensity. We have to find electric field intensity. So first of all, to find the electric field intensity, we have to know the electric field on Q charge. Okay, the Q charge is on the center. Okay, this is the Q charge. And after that, we have to find electric field of sphere also. Okay, so we know that electric field of the sphere is 0. Okay, it is clear on the first equation. Electric field at the center of uniformly charged hollow sphere is 0. So because of this, electric field of the sphere is 0. And the electric field due to Q charge is kq upon r square. Okay, it is kq upon r square because the value of electric field intensity is kq upon r square. Electric field due to sphere is 0 because point lies inside the charged hollow sphere. If this point is not inside the sphere but outside the sphere, the electric field is not 0, but it is present on the inside charged hollow sphere, so the electric field is 0. Okay, so the net value is, or we can say that EA vector is equals to kq upon r square. Next, the next question is electric field. We have to find electric field intensity at point B, and B point is situated outside the center, as you can see in the diagram. So this point is situated outside at the center. Okay, so the electric field not be 0. So if the net electric field on point B is electric field due to sphere and electric field due to Q charge is equals to the sphere. For sphere, charge is capital Q, and for outside this, the value of Q is small q. Okay, so now we can put the values, which is kq capital Q upon r square, and this is the vector form. So we multiply this by r cap, and we have to plus the electric field on Q charge due to point B. Okay, we have to find electric field on Q charge also, and we have to find electric field on sphere due to B. Okay, so it is due to B, so the electric field on sphere doesn't 0 because it is due to point B now. If we have to find electric field due to point A, it is 0 because it is inside the center. But B is not inside the center, so the electric field on the sphere is not 0. So the value of electric field inside the sphere is K capital Q upon r square multiplied by r cap plus KQ upon r square multiplied by r cap. Okay, so K is common in both the electric fields. Q plus capital Q plus small q and r square, and r cap is also common. So we will get this value. Okay, we will get this value, and this is the electric field at point B. Okay, students, I hope you understand this all equation number 1, 3. Okay, so coming to our next topic, which is properties of electric field line. Okay, what is the properties of electric field line? So first of all, I'll show you what is electric field line. Electric field lines look like this. They can look like this. Okay, so now what is electric field line, or we can say that electric line of force. Electric line of force. Okay, this is also known as electric line of force. Electric line of force. Okay, so the first property is the field lines never intersect each other. It is the very important property, and you have to know this. The electric field lines never intersect each other. They never intersect each other at any point. Why? If they intersect at any point now, they give two directions. Okay, electric field lines, if they intersect each other now, they give two directions, which is not possible. So they never intersect each other. Second point, the field lines are perpendicular to the surface of charge. All the electric field lines are perpendicular. I can show you with the help of this diagram. All the electric field lines are perpendicular to the surface of charge. Okay, all the electric field lines are perpendicular to the surface of charge. Third point, the magnitude of charge and the number of field lines both are perpendicular to each other. Okay, the magnitude of charge and the number of field lines, okay, both are proportional to each other. That means if the number of field lines increase, the magnitude of charge is also increase. What I'm saying, if the number of field lines increase, the magnitude of charge will also increase. So we can say that the magnitude of charge and the number of field lines both are perpendicular to each other. Okay, students, I hope you understand this point. Okay, so the next point is the start point of field line is at the positive charge and the end at the negative charge. That means the electric field line or electric line of force, the starting point is positive charge and the ending point is negative charge. With the help of diagram, we will understand this point. For the field lines to either start or end at the infinity, a single charge must be used. Okay, field lines either start or end. If it will be start at infinity or if it will start from end, but a single charge must be used. Okay, only single charge must be used. You can understand these 2 points with the help of this diagram. First of all, what is electric field lines attraction and repulsion? Electric field lines always point away from a positive charge and towards the negative point. So in fact, electric field originates at a positive charge and terminate at a negative charge. You can see in this diagram, from positive charge, all the electric line of force away, and for the negative charge, all the electric line of force coming towards the negative charge. So we can say that electric field originate at positive charge and terminate at negative charge. What I'm saying, electric field lines originate from positive charge and terminate at negative charge. Okay, you can see it is originate from positive charge. In this diagram, it is terminate from positive charge. It is in the direction of negative charge and it is terminate at negative charge. Okay, so also field lines never cross each other. If they do, I'm clearing this point. Okay, what it is? Also, electric field lines never cross each other. If they do, it implies that there are two different directions of electric field at that point. But this is impossible since electric fields add up vectorially at any point. And remember that a field line is drawn tangentially. Okay, we can draw a field line tangentially like this. Okay, this is the electric field line of force. We can draw this tangentially, tangent to the any electric line of force to the net electric field at a point. Thus, electric field lines never intersect each other or another. So, when the field is stronger, the field lines are closer to each other. Okay, this point is very important. When the electric field lines are stronger, that means electric lines of force are close to each other. You can see in this diagram, all the lines are very close to each other. So we can say that the electric field of this electric line of force are very stronger. Okay, what I'm saying, when the electric line of force are very closer, we can say that the electric field is very stronger in this. Okay, so this is the positive charge and all the rays are originate from this positive charge. Okay, this diagram. So, different patterns of electric field lines. Electric field lines can never intersect each other, but they follow different patterns. You can say they follow different patterns. The patterns are like they are originate from the positive charge, they terminate from negative charge. In this diagram, the pattern is different. In this, it is also different. Okay, so this is different patterns of electric field line of force. Okay, and one point, electric field lines are symmetrical to line joining two charges. Okay, there are two charges And okay, you can see this diagram. Electric field lines are symmetrical to the joining of two charges. These are two charges, positive charge and this is negative charge. So these lines are symmetrical now. These lines are symmetrical to the line. This line is joining the two charges and all the lines are symmetrical to this line. So we can say that electric field lines are symmetrical to the line joining two charges. Okay. So I hope the electric field lines are clear. What is electric field lines or electric line of forces? The field lines never intersect each other. The field lines perpendicular to the surface of charge. The magnitude of charge and the number of field lines both perpendicular to each other. The start point of the field line is at the positive charge and the end point is at the negative charge. For field lines or to either start or end at the infinity, a single charge must be used. So this is the basic properties of electric field line. Okay, so our next important topic of this chapter is electric dipole. Okay, so this is the question based on the electric field line. Okay, you can see in this question there is a electric field line of forces and these are originated from Q1 and terminate from or at Q2 charge. Okay, these are originated from Q1 charge and these are going or end at Q2 charge. So we have to find the electric field line. That means we have to find Q1 upon Q2. Okay, so how we find this? The Q1 and Q2. We have to count the electric field line. Okay, so the electric field lines which is originate from Q1 is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, the number of Q1s are 12. I'm taking the new pen. So Q1 upon Q2 is Q1 is 12 and our Q2 is 1, 2, 3, 4, 5, 6, 7, 8. So it is 8. But the sign of Q2 is negative because it is negatively charged. We can say this Q1 is positively charged and Q2 is negatively charged. Why? Because all the lines are terminate at point Q2 now. So it is negative because all the electric field lines are terminated negative charge. So the sign is negative and we can say that minus 3 by 2. The answer is minus 3 by 2. Okay, I hope you understand. Okay, so this time we can find the electric field line. After that, our main important topic is electric dipole. Okay, electric dipole. What do you understand by electric dipole? You can see the diagram also. What is electric dipole? We can say that an electric dipole is defined as the couple of opposite charges q and minus q separated by a distance d. By default, the direction of electric dipole is phase is always from negative to positive charge. So the midpoint q and minus q is called the center of the dipole. So the simplest example of an electric dipole is the pair of electric charges of two opposite signs and equal magnitude separated by d distance. Okay, so the basic and simple definition of electric dipole is an electric dipole is a couple of opposite charges. Okay, what is electric dipole? It is a couple of opposite charges q and minus q. Okay, it is a couple of positive charges. You can see here now, this is the plus q charge and this is minus q. Okay, this is plus q and this is minus q and they are separated by d distance. It also can be 2D, it also can be 4D, but we are representing this by d distance. Okay, the basic definition is electric dipole is defined as couple of opposite charges q and minus q, which is separated by the distance. So, by default, the direction of electric dipole in space. What is the direction of electric dipole? Firstly, you have to learn the definition, that is couple of opposite charges. Second, you learn what is the direction of electric dipole, because when you solve the numericals, this is very important in that. What is the direction of electric dipole? So always remember, the direction of electric dipole is always from negative charge to positive charge. Okay, the direction of electric dipole is negative charge to positive charge. We can say that electric dipole is very positive, so it always goes from negative to positive. Okay, we remember it like this. The midpoint q and minus q is called the center of the dipole. The center of the dipole is, if the distance is d, we can say this is d by 2 and this is d by 2. So, the electric dipole is a pair of electric charges of two opposite sign and equal magnitude separated by distance. So, always remember, in electric dipole, the magnitude of charges are always equal. Okay, the magnitude of charges are always equal, but they are opposite in sign. Okay, that's why we can say these are the couples. These are opposite in sign, but their magnitude is always equal. That means if the charge is q plus q, so the other charge is minus q. Okay, if the charge is plus 2q, other charge is minus 2q. Okay, the magnitude is always same, and distance between them is d. Okay, so the formula of the magnitude of an electric dipole is given as p vector is equals to qd vector. Okay, p vector is equals to qd vector. Here p vector represents the electric dipole. Okay, it represents electric dipole. Okay, and q represents the charge and our d represents distance. Okay, here the p vector and d vector denotes that the value of electric dipole and distance. Sorry, the direction of electric dipole and the direction of distance is always same. Okay, p vector and d vector, what they say is the direction of electric dipole and the direction of distance is always in the same direction. Next, the direction of electric dipole moment. What? The direction of electric dipole moment. So the first of all, what is electric dipole moment? It is a vector quantity. Which quantity? Electric dipole moment is vector quantity. You can assume by this formula, because over the electric dipole, that is represented by p, is a vector sign. Okay, if we are using vector sign, we can say that it is a vector quantity. So the electric dipole is vector quantity. It has a direction. It is a definition direction, which is from the negative charge to positive charge. Okay, it is a defined direction. All the electric dipole have a defined direction, which is negative charge to positive. You can see here the direction of electric charges from negative charge to positive charge. So though it is important to remember that is convention of direction is only followed in physics. In chemistry, the convention is taken to be opposite. Okay, these sign convention, which is negative to positive, this sign convention only follow in physics, but in chemistry the convention is taken to be opposite. That means from positive to negative. Okay, in chemistry positive to negative, but in physics the direction of electric dipole is taken negative to positive. So the line along the direction of an electric dipole is called axis of the dipole. Okay, so the line along the direction of electric dipole, is called axis of the dipole. What is called? Axis of the dipole. Okay, I hope you understand all the terms related to electric dipole and the direction and what quantity it is It is a vector quantity. The direction is from negative to positive. The direction of an electric dipole is called the axis of the dipole. Okay, the line along the direction of electric dipole is axis of the dipole. The formula is P vector is equals to Q multiplied by D vector, where P vector represents the electric dipole and Q represents the charge and D vector represents the distance. Okay, so there are some questions related to electric dipole concept. Your first question is, an electric dipole is placed in a uniform electric field. Okay, there is an electric dipole. That means there's a couple of charges which is same in magnitude but opposite in direction is placed in a uniform electric field. So we have to find the net electric force on the dipole. What is the net electric force on dipole? Okay, so your option number A is it is always 0. Option number B is depends on the orientation of the dipole. That means what is the orientation of dipole? It depends on that. Okay, so the C option depends on the dipole moment. And the D option is always finite but not 0. What you thought? What option is correct? Okay. What option is correct? So I can say that the option is always 0. Why? Because dipole consists two equal and opposite charges. We know that a dipole consists of two and opposite charges, two equal and opposite charges. So the value of charges is plus q and minus q. And if we want to find the force on that, what question asks? The net electric force on the dipole. So the net electric force due to plus q and minus q charge which is placed in a uniform electric field is, the value of force is QE. And due to plus q charge it is plus QE, and due to minus charge the force is minus QE. It is due to plus q charge, it is due to minus q charge. If we add them together, we will get the value 0. Okay, minus 9. The minus. Cut out, the value is 0. So we can see that electric dipole is placed in a uniform electric field. The net electric force on the dipole is always be 0. Understood? Why is it always 0? Because the charges are opposite to each other but equal in magnitude. So their magnitude will cancel out to each other and we will get the value of 0. So we can say that it is always 0 in uniform electric field. Okay, students, I hope you understand this point. Next, what is the... Okay, so question number 26. QA is equals to... there are two charges, the QA charges and QB charges, which is given in the question. So, QA charges C at A and QB charges at point C is this. So, we can say that we have to find the electric dipole moment of the system. So, this is the electric dipole. This is the electric dipole. And there are 2 points on the electric dipole, which is A and B. Okay, A and B. In this point, the charge is plus 2.5 multiplied by 10 raised to the power minus 7. At 8 point B, the charge is QB, which is minus 2.5 into 10 raised to the power minus 7. So, at point A, we have a dimension 0, 0, minus 15. And at point B, we have the dimensions 0, 0, 50. Okay. So, we have to find the electric dipole moment. And what is the formula of electric dipole? First of all, electric dipole is represented by P. And the formula is Q multiplied by D. Here Q multiplied by D, D is the distance. So the charge is always equal but opposite in sign. The charge on A and the charge on B is equal, which is 2.5 into 10 raised to the power minus 7, but they are opposite in magnitude. So the charge is, the value of charge is 2.5. We can write here. Cut. So P 2.5 multiply by 10 raised to the power minus 7 multiply by distance. What is the distance? How we will find the distance? This is, you can saw in the options, it is k cap, k cap, k cap. Why it is k cap? Because the magnitude is 0 in x axis and y axis. So on z axis, that means it is the value of k cap, because of z axis is not 0. It is 15 and minus 15. So 15 plus 15 is 30. So we will take the distance 30, and if we multiply this, we will get the value 75 multiplied by 10 raised to the power minus 9, and according to the question, we will get the value 10.5 into 10 raised to the power minus 8 centimeter in k cap. Okay, in k cap. So I want to ask you, what is the direction of this electric dipole movement? It is always from positive to negative. Okay, it is always from positive to negative. That means it's always from positive to negative. Okay, so our answer is 7.5 into 10 raised to the power minus 8 centimeter. Okay, so I hope students, you understand this question. This is very interesting question according to the electric dipole movement. Now I have one more question for you guys. Find the dipole moment of the combination of the charges as shown in figure. You can see in the figure, there are the combination of charge. Okay, there are charges which is Q and minus Q, 2Q. Okay, and we also have given the dimensions on that one. So what we have to find? We have to find the dipole moment due to the combination of charges. Okay, so how we will find the electric dipole moment? So first of all, we can break this diagram. How we can break this? Like this. This is Q. This is minus Q charge. This is Q charge. This is also Q charge. This is 2Q, na? So Q and Q. And this is minus Q. So there are two dipole moments. There are two couple charges, na? Plus Q minus Q, plus Q minus Q. Okay, and they are separated by the distance A, and here is also A. So we know that the dipole moment between this Q and minus Q and Q and minus Q is P. Okay, the dipole moment between these two charges is P, and these two charges is P. Okay, so what we have to find? We have to find the dipole moment of the combination of the charges. Okay, combination of the charges. That means we have to find the net resultant of this dipole moment. Okay, due to both these dipole moments, we have to find the net dipole. So the net dipole moment is root 2p. Okay, because of these two charges, the net dipole moment is root 2p, and the value of p is, that means, first of all, what is p? P is a dipole moment, and what is the formula of dipole moment? E is equals to q into d, and here d is distance, and distance is given a. So in the place of d, we can, first of all, we have to write root 2 upon q d, and d is Here D is the A distance. So we can write root 2 is equals to QA, and it is the answer also. So the option number D is correct, which is root 2 AQ. We can write AQ or QA, both are equal. So option number D is correct answer. Okay, students, I hope you understand this. Now we coming to our next topic, which is electric field due to dipole. Okay, now we have learned how to find electric field on the axis of the dipole. There are two cases. Okay, there are two cases. First is because the axis of dipole, and second is on the equatorial line of the dipole, that means bisector of the dipole. But first we have to find the electric field on the axis of dipole. Okay, on the axis of dipole. Okay, so you can see in this diagram there are a dipole, okay, which is the minus q charge and plus q charge, and they are separated by the distance 2l. Okay, these are separated by 2l distance, and the distance between the center of the dipole and point P charge is r. Okay, the distance between the middle of the dipole moment and the point P charge is r. So if we want to find the distance between plus q charge and P, it will be r minus L, because the distance from this point to this point is r, and the distance from the center of the dipole and plus q charge is L. So we can say this is the r minus L. Okay, so on point P we have to find the net electric field. Okay, how we will get the formula? On point P we have to find the net electric field due to both charges, due to plus q charges and due to minus q charges. So due to plus q charges, that means there are two electric field on point P. Okay, the two electric field, one electric field on this side and one electric field is in this side. So electric field E1 is on this side and electric field E2 on this side. Okay, one electric field, because the electric field due to the electric dipole is E1, and it is from negative to positive. Okay, it is from negative to positive. So E2 is this electric field. Okay, so there are two net electric field, and we have to find net electric field. So the formula is E2 minus E1. Okay, if we want to find the net electric field, the formula is E net is equals to E2 minus E1. Okay, so the value of E is, we have charges plus Q and minus Q. So the value of E2 is KQ upon, first is this, E2 is this, plus Q2 minus Q, because first the electric field due to plus Q charge on point P is r minus L. This is the distance r minus L. So we can write r minus L ka whole square and minus distance KQ charge is r plus L. Understand this point? What we are done, we have to find the electric field at point P due to both the charges plus Q and minus Q. And if we want to find the electric field due to plus Q charges, the value is KQ upon r minus L, because the distance between Q and P is r minus L. And if we want to find, and this is the E2. If we want to find the electric field due to minus Q charge, the sign is minus first of all, and KQ is the KQ upon r plus L, because the distance is, this is the r and this is L. Okay, so r plus L ka whole square. Now what we will get, if we will solve this equation, we get the value E net is equals to, we will get what, 2 K P R. P is the vector form, and this is r square minus L square ka whole square. What we will get? 2kpr upon r square minus L square ka whole square. Okay. So the net electric field on the axis of dipole is this. Okay. So on next sheet, I'm explaining this point. What value we will get? E net is equals to 2kpr, the vector form, upon r square minus L square e power whole square. This is the general expression. Okay. This is the general expression. This is the general expression on the axis of the dipole. But if we are talking about small dipole, which is very important. Okay, if we are talking about small dipole, because 95% are coming from this small dipole. Okay, this is very important expression of this chapter, because 95% of the question coming from this expression. Okay, so small dipole, for small dipole, there is a condition that means r is very greater than L. Okay, r is very greater than L. So L is very negligible in compared to r. So we can put the value of L square is equals to 0. Okay, we can put the value of L square equals to 0. Why? Because the L is very small compared to R. This is the condition. If we apply this condition, what value we will get? Let's see. E net is equal to 2k R and R square का whole, because it is 0 na, so R square का whole square, so 2k factor R की power 4, R is cut from this, and the final value of this expression is 2kp vector upon R cube. Okay, what we will get? 2kp vector upon R cube, and this expression is very important. You have to learn 2kp vector upon R cube. What value? 2kp vector upon R cube. This is the value for small dipole. Okay, this is for small dipole. Okay, student, understood? E is equals to 2kp vector upon R cube. Okay. So our second case is on the equatorial line of dipole. That means perpendicular bisector of dipole. You can see here, this is the dipole, minus q plus q is separated by 2L distance. We have to find the electric field. That means perpendicular bisector of dipole. How we will find this? So we have to make a diagram for this. So we have to find electric field at this point P due to minus q charge and plus q charge. Okay, what we have to done? We have to find electric field on point P due to minus q charge and due to plus q charge. So due to this, the electric field on point P is in the direction of this, because it is negative charge. So it is towards the direction of negative charge. Okay, and due to plus q charge, it is in this direction. Okay, it is in this direction. That means away from the positive charge. So we have to find the net electric field between them. This is E1, this is E2, and this is E1. Okay, and we have to find E net. And the angle between them is theta. Okay, understand what I'm doing? We have to learn net electric field due to minus q charge and plus q charge. So the angle between E1 and E2 is theta. Okay, So first of all, we have to find electric field E1 and the value of electric field E1, which is KQ upon the distance. Okay, for this we have to find the distance. We have a value of perpendicular is R. Okay, and the base is L. So with the help of this, we can find the hypotenuse now. With the help of Pythagoras theorem, we have to find hypotenuse, which is R square plus L square. Okay, in same, this is same in this also, which is R square plus L square. Okay, so R square plus L square ka whole square. Okay, this is the equation, and if we solve this, what we will get? KQ upon R square plus L square. This is the value of E1, and the value of E2 is also same. How? Magnitude is same now. And if we will do the square, the negative sign is also positive. So this is same. KQ upon R square plus L square. This is the value of E2 and E1. So if we solve this, what we will get? First of all, we have like this. We have a theta. We have the value theta. This is E2. Okay, this is E1. This is E2. And this is our net electricity. Okay, so these are the cost component. Okay, this is the cost components of electric field, and the sign components are cancel out each other. So the E nat and the electric field or net electric field is 2E cos theta. Okay, this is 2E cos theta because the sign components are cancelled out with each other. Now we have the value 2E cos theta, and if we will find the general expression due to the perpendicular bisector of the dipole, we will get the general expression is E perpendicular minus Kp upon R square plus L square e power 3 by 2. Okay, so this is the general expression for perpendicular bisector of electric dipole. This is same as that. Now you can see this. In this, the value is 2 kp vector upon r cube, and in this the value is minus kp upon r square plus l square. So this is the general expression. But if you want to find the famous expression, this is the general expression. But if we want to find the famous expression, we have to derive the formula for small dipole. Okay, for small dipole, what is the condition? For small dipole, we will take the value of R very greater than L. Okay, we have to take the value of R very greater than L, and the next equation is minus Kp. Okay, minus Kp upon R square by 3 by 2, and if we solve this, minus Kp upon R cube. This is the expression. Okay, this is the expression for perpendicular bisector of electric dipole, minus Kp upon R cube. It is something same like that, but not totally same. We can say for axial on a axis of dipole, the value of E is 2 kp upon r cube, and for perpendicular bisector, the value of A is minus kp upon r cube. Okay, students, I hope you understand this formula. Okay, so there are some questions which is based on these formulas. Is a point Q lies on a perpendicular bisector of an electric dipole of dipole moment P. If the distance of Q from the dipole is R, which is much larger than the size of the dipole, then electric field is. Okay, so what kind of dipoles? A point Q lies on a perpendicular bisector. For the perpendicular bisector, what is the value? The value is minus Kp upon Rq. Okay, so first we have to write the value of electric field from perpendicular bisector. Perpendicular bisector is minus Kp upon R cube, and for the axis it is 2 Kp upon R cube. And a point Q lies on the perpendicular bisector of electric dipole of dipole moment P if the distance of Q from dipole is much larger than the size of dipole, then the electric field at Q is proportional to. Okay, so we have to use this formula. Okay, we have to use this formula because this is the formula for perpendicular bisector, and our electric field is directly proportional for P, and it is directly proportional to R cube also. We can write E is directly proportional to R minus cube. So the option number D is correct. Okay, so this question it is come in 1998 on IIT paper. So our value of electric field is directly proportional to P, and the value of electric field is also directly proportional to 1 upon R cube. Okay, students. So our next question is the electric field due to dipole at a distance r from its center in axial position is E. Okay, so we have to use the formula of dipole moment on axis. Okay, what is the formula? It is 2 Kp upon R cube. Okay, we can write here E is equals to 2 Kp upon R cube. If the dipole is rotated through an angle 90 about its perpendicular axis, so the electric field at the same point will be. So we can rotate the electric dipole. This is our electric dipole. Okay, this is our electric dipole. If we rotate this, the angle will, if we rotate it from the angle of 90 degree, we have to find the electric field at the same point. Okay, so electric field. Okay, so about the perpendicular axis, the electric field at the same point will be. Now, this is the formula for perpendicular bisector. See, this is the formula of the axis. Because of axis and to perpendicular bisector, we have this form. What? E is equals to minus Kp upon R cube. Okay, so if we make a ratio of this, what we will get? We will get E by 2. What we will get? It is cancel out from each other, and we will get E by 2. That means electric field at the same point will be E by 2. Okay, what we will get? E by 2. I hope you understand. When we will make a ratio of these electric fields, that is cancel out totally, but only 2 is remaining. So E by 2. Okay, so our next topic is torque on an electric dipole in an uniform electric field. Okay, so what is our next topic? Torque on an electric dipole in an uniform electric field. So first of all, if you want to find the electric field on a torque on an electric dipole in a uniform electric field, so first of all we have to know what is torque. Okay, what is torque? Torque is a measure of the force that can cause an object to rotate about an axis. Okay, what I'm saying, torque is a measure of the force. That means torque is a kind of force. Okay, we can see that torque is a kind of force that can cause on an object. Okay, there is an object which rotates about their axis. Okay, so the force is exerted on this. We can say that is torque. Okay, student, understand what is torque? It is a measure of the force that can cause rotate about an axis. And second point is torque is the vector quantity. What? Torque is the vector quantity. That means it gives magnitude and it gives direction also. Okay, it gives magnitude and it gives direction also. So the following formula is used to determine the torque vector's magnitude, which is T is equals to F multiplied by R. What? F multiplied by R. So torque is equals to F into R into sin theta. These two are the basic formulas of torque. F means force and R means position vector. Uh, Here, R is the position vector, that is a vector from the point about which the torque is being measured. Okay, a vector form a vector from the point about which the torque is being measured to the point where the force is applied. Okay, what? R is the position vector, a vector from the point. Okay, it is a vector from the point about which torque is being measured to the point where the force is applied. Okay, clear what is the R? Next, F is a force factor. Okay, these are the all are the vectors because torque is a vector quantity and this is that's why we are measured it is a vector. The force F is a force factor. Theta is angle between the force factor and lever arm factor. Okay, theta is the angle between force and lever arm factor. So here, clear what is R, what is F, what is torque. Formula of torque is T is equals to F multiplied by R. Okay, T is equals to F multiplied by R. Okay, so the derivation of torque on an electric dipole is, we have to find the derivation of torque on an electric dipole. Okay, so now suppose a dipole whose charge is plus q and minus q from a dipole because they are separated by d distance. If we place the dipole in a uniform electric field on strength E, okay, this is the electric field, the strength is E, then the angle between electric field and dipole moment is theta. Okay, the theta is the angle between dipole moment and electric field. Okay, this is the dipole, couple of dipoles which is placed in the electric field and the angle between electric field and dipole moment is theta. Okay, now what is the formula of torque? First of all, we have to find the force on plus q and minus q charge. Okay, the force on plus q charge, F factor is equals to plus QE factor. Okay, F factor is equals to plus QE factor, and F factor due to minus charge is minus QE factor. Okay, minus QE factor. So the components of force perpendicular to the dipole are, these are the component of force which are perpendicular to the dipole is F perpendicular to the dipole, this is due to minus charge is plus QE sin theta, and the component of force due to minus Q charge is minus QE sin theta. Okay, understand what I'm saying? The components of force perpendicular to the dipole due to plus Q and minus Q charges plus QE sin theta and minus QE sin theta. Now, the value of torque is, what is the value of torque? It is F into R. Okay, and what is the value of force? QE sin theta. Okay, so we know that torque is equals to QE sin theta. So this is dipole moment is given by, if If the torque is T is equals to PQ is sin theta because of the components, then we know that P is equals to it is electric dipole because electric dipole is used in this now. So P is equals to Q multiplied by T. And if we put the value of Q, that is Q is equals to P upon T, we will put this value on this equation. This is D and the value is P by D E sin theta. D is cut from D and what will we get? Torque is equals to P E sin theta. Okay? Torque is equals to PE sin theta and here there's a negative sign. Why? Okay, I'm giving the reason. As can be seen from the equation above, the torque is the cross product of dipole moment and electric field. What it is? It is the cross product of dipole moment and electric field. Okay. Then dipole moment and electric field, and the direction of the dipole moment is from the negative to positive charge. We know what is the direction of dipole moment? It is from negative to positive charge. So, if the direction of electric field is positive, then the direction of torque is negative. Okay? Because we know the direction of dipole moment, it is from negative to positive charge. And if we take the direction of electric field is positive, then the direction of torque is negative. That means torque is here negative. Or we can say this, the value of torque in the vector form is T vector, or it is torque vector, T vector multiplied by E vector. Okay, it is in the vector form. Now we can also write this form, which is P E sin theta. Okay, if we take a mode of the torque, what will we get? We will get the positive value of torque, which is P E sin theta. Okay, so this is the derivation of torque on an electric dipole. Understand what we are doing? This is the derivation of torque due to or on an electric dipole. What we are doing? Suppose a dipole charge plus Q and minus form a dipole because they are separated by d distance. And if we place this dipole on a uniform electric field of strength E, the angle between electric field, you can see the angle between electric field and dipole moment is theta, and we know the formula of torque, which is P is equals to Fr, which is R is the position vector, F is the force vector, and if we want to find the components of torque, the formula is P is equals to Fr sin theta. Okay, so the torque is dQE sin theta. That is the cross product of dipole moment and electric field. Okay, the dipole moment and electric field, because T is equals to QD. QD is the what QD represents? QD is equals to T and it is the electric field. So we can see this. It is the cross product of dipole moment and electric field. And if we will put the value of Q in this, D is cut from D and we will get minus P sin theta, and here minus sin theta, the direction of electric field is positive. Okay, what it is represent? The direction of the dipole moment is from negative to positive. So if the direction of electric field is positive, then the direction of torque is negative. So we will put the sign of negative here. And if you want to form a positive, what we will do? We will do a mode of torque and we will get a positive value, which is P sin theta. Okay, students? So I hope you understand this point. Okay. So the question, angle between electric dipole P and the electric field E when the dipole is in the stable equilibrium. What is the question? The angle between electric dipole moment P and the electric field E when the dipole is in stable equilibrium. What is the answer? The answer is 0. Okay. So you can say that it's stable equilibrium. Okay, in stable equilibrium, the angle between electric dipole moment and electric field is 0. Okay. Distance. Okay. So I hope you understand what I'm saying. Thank you for the class.